Okay, how are you guys doing? We had our test yesterday. I was just saying, it's too bad our test wasn't on Thursday, then we could all skip Friday, right? We'd be like, are you going to skip Friday? No. But I could have some other video, put some other, like have another video of another lecture up there, put some other words on it, you know, confuse anybody who's checking up on me. What? Record the previous class again, right? Right? Wow, it seems like we did the same stuff twice in a row. Who knew? Who knew? What? What was that hard, right? All right, so you should get your test back by tomorrow, hopefully. That's what I'm hoping. And some people's grades are up right now, right? And then we'll come back on Friday, and then spring break. Is anybody going any place fun? Oh, wait, you have a question. Or are you cheering for spring break? Oh, a question. Okay, what's your question? Yeah, what's the derivative of log base 3 of x? Is that?
Yeah, actually we can use like the log rule and then like another than 3 is the
The derivative of natural log of 3 is constant, but it's a constant multiple rule. I'll put another step in here. Equals 1. Can you see all the way down here? People on here. Okay. Log base 3 of x is equal to d over dx, natural log of x, natural log of 3, right? Is equal to d over dx 1 over natural log of 3 times natural log of x, right? Now this is a constant, so it can be pulled out of the derivative sign. Equals 1 over natural log of 3 over dx of natural log of x, right? Equals 1 over natural log of 3 times 1 over x equals 1 over x natural log of 3. Now, I do not advise putting all these steps in here. I just put all the steps in so you could see how I got there. I mean, seriously, what I would do is I'd say equals this equals 1 over natural log of 3 times x. That's how many steps I would put in. Okay. The derivatives are tricky, right? The derivatives are tricky, but you know what I've been telling. I mean, the derivatives were going to be hard, right? And then we had a logarithmic differentiation. We had an implicit differentiation. We had a max-min problem, and we had a related rates. And it came down to the Pythagorean theorem. Related rates did, right? Okay. Let's go on. I'm supposed to teach you something new today, so I'll try. I'll do my best. Here we go. One of the, before computers were around, one of the huge points of calculus was curve sketching. To give you an idea what curves look like. Curve sketching. And I can, if I was a betting man, I would bet on your next exam they're going to ask you to sketch a curve. Now, if I were you, I'd be thinking, how hard can that be? We all have graphing calculators. I just won't pay attention, and I'll use my graphing calculator, and that's how I'll solve the problem. That's what I would think. You know, it's the smart thing to think. Okay, why would I pay attention to this if I have a graphing calculator? Well, we're going to put if they write the exam like I would, which I have no idea, they're going to do something that's going to make it impossible to use a graphing calculator. We'll talk about that in a second. But let's just go through the basic idea. Okay, curve sketching. There's a procedure. Now, I made up this procedure, so if you think it sucks, then, well, I just made it up. And you can make up your own procedure, okay? This is just sort of like, Bart, what do you do when you sketch a curve? The first thing, here's what we're going to do. I'm going to have a curve I'm sketching, and we're going to go through and do it. We're just going to do an example right away. We're going to sketch sketch 2x cubed minus 3x squared minus 12x. That's what we're sketching right there. The first thing I do, here I'll number them. The first thing I do is I try to find the y-intercept. Okay, and this goes back to my philosophy of do what's easy first. Finding the y-intercept is easy. Find y-intercept. That's 0, f of 0. To find the y-intercept, you just plug in 0. Okay, so what's the y-intercept here? Yeah, this is f of x equals, well, f of 0 equals 0. So I can start to plot my curve immediately. X, y. Here's my y-intercept. It's a good place to start. Okay. 2. Find candidates for vertical asymptotes. What's a vertical asymptote? How do you get a vertical asymptote? What usually happens to get a vertical asymptote?
It's undefined.
It's undefined, and how are functions usually undefined? Division by 0. Division by 0. Now, there are some functions that might not look like they have it, like tangent. But tangent does, right? Because tangent is equal to sine over cosine. And so where cosine equals 0, that's where it has vertical asymptotes. And so this one's fine. This one doesn't have any vertical asymptotes. 2, 3. Compute f prime and f double prime of x. Compute now look, I'm ordering this really kind of in like how easy to hard. How easy it is to do something versus how hard it is. It's easy to plug in 0. It's easy to look and say, do I have any division in here? You just look, right? And then here you say, well, compute f prime and f double prime. Well, so f prime of x is equal to 6x squared minus 6x minus 12. Did I do that right? Excellent. F double prime of x is equal to 12x minus 6. The great thing about derivatives is that typically, if you're working with a polynomial, they make the polynomial simpler. F double prime is more simple than f prime. So we want to be working with the derivatives as fast as possible. We don't want to be working with this original function, which is more complicated. This is like a standard trick that somebody does when they cook up questions. They say, let's start off with something complicated, that when you take its derivative, it gets simple enough that the student can work with it. If they try to work with the function directly, it's usually too hard. All right. What do we do next? Compute f double prime. Oh, find the critical points. 4. Find critical points. Find critical points. Find critical points. And where are the critical points? Where the derivative is equal to 0 or it's undefined. Now, this derivative is defined everywhere, so it's just where it's equal to 0. And what type of equation is this right here? It's quadratic, right? Started with a cubic, took its derivative, we got a quadratic. We can solve quadratic equations pretty easily. So, critical points. Critical points, let's see. I want to solve 6x squared minus 6x minus 12 equals 0. Can anybody tell me what to do to simplify this right off the bat? Yeah. factor out the 6, you divide everything by 6, because 0 divided by 6 is 0, right? And so I get x squared minus x minus 2 equals 0. All right. X squared minus 2 plus, that's x minus 2 times x plus 1. Is that right? Awesome. And so we have critical points at x equals 2 and x equals negative 1. And you know what I like to do when I'm trying to sketch a curve? What I like to do is I like to put my critical points on as like horizontal lines. So if here's negative 1 and here's, don't erase on your paper, but I'm going to draw this bigger. I want this to be bigger. Oh. The y-intercept is here. That's a point on our curve. And the critical points are at x equals negative 1, which I'll put right here. And x equals 2. 2, negative 1. And what are the critical points? What do they hopefully tell us? Yeah? Where the slope is 0. And where the slope is 0 is where we think we might have a max or a min. And that's why I drew these lines here, because I'm kind of imagining, you know, these things kind of moving up and down. They could be anywhere along that line. All right, so find critical points. Looking good. 4, 5. Use the second derivative test to locate local extrema. Use second derivative test to locate local extrema. And find where the function's increasing or decreasing. That says function, fxn is increasing. And here's where the magic really happens, right? So minus 1. So I plug minus 1. We got to plug the critical points into the second derivative and hope that they're not 0. And so plug x equals minus 1 into f double prime of x. And so I get 12 f double prime of minus 1 is equal to 12 times minus 1 minus 6. And is this number positive or negative? It's negative. This is negative. It's negative, and negative means that you're concave down. Concave down. So that tells me that somewhere here, if this is concave down, it tells me that the function is going up to this point, right? And it's got to be going down here. This is concave down. You understand what I'm saying? And now, this is good. And now, let's see. It should be, what about if we plug in 2? So f double prime of 2 is equal to 12 times 2 minus 6. This is positive. Positive means concave up, the k part's on the up, concave down, right? So concave up, aha, so that works with this. It's going to be something like this, right? So then your function is going to be increasing over here, right? Okay, that's great. That's great. And look, since I know I can plug in, what is f of negative 1? F of negative 1. Well, negative 1 cubed is negative 1, so that's minus 2. Minus 3, that's minus 5, right? Plus 12. 7. So f of negative 1 is equal to 7. It will be up here. So this is 7, right? And what is f of 2? Well, 2 cubed is 8. Times 2 is 16. So that's going to be 16 minus 3 times 4. 16 minus 12 is 4. Oh, geez. What's 4 minus 24? Oh, that's not so bad. It's minus 20, right? Is that right? I think that's right. 4 minus 20. Yeah, I agree. So this is going to be down here someplace at minus 20. Aha. And we know the function is concave down here, so it's going to look like this sort of, and it's concave up here, so it's going to look like this, right? Around this part. All right. What else? Does anybody know what we have? Critical points. What are like critical points? Inflection points. So 6. I think my number 6 is find inflection points, right? Yeah, find candidates for the inflection points. Find candidates for inflection points. Find the candidates for the inflection points. Now, remember, critical points are where the derivative is equal to 0 or undefined. Inflection points are where the concavity changes. All right? And so this is also where the second derivative is 0. So to find the inflection points, you've got to check for the second derivative. Well, you should check to be undefined too, I guess. But f prime of x is equal to 0. F double prime of x, so that's 12x minus 6. Oh, where is 12x minus 6 equal to 0? Equals 0. 12x equals 6. X equals 1/2. All right, and now, so we need to know, is this an inflection point? Remember, that's where the concavity changes. So we want to know, is the second derivative positive to the one side and negative to the other? Is that obvious? What type of function is the second derivative here? It's a line. So it's going to be positive to the one side of the root and 0 to the other. If it was a parabola or something, maybe you could have something bad happening, but not in this case. So this is an inflection point, and it's x equals 1/2. So this is an inflection point. 1/2 is about there. That's an inflection point. We need to know, what is f of 1/2? Well, this one's hard enough that maybe we should go ahead and, I'm running out of space. F of 1/2 is equal to, what's f of 1/2? Oh my God, what's 1/2 cubed? 1/8. So it's going to be 2 times 1/8. And then we're going to have minus 3 times 1/4 plus 12, minus 12 times 1/2. That's minus 6. This is 2/8 minus 3/4 minus a 6. Oh, geez. That's equal to 1/4 minus 3/4 minus 6. Is that right? Okay. 1/4 minus 3/4, that's equal to minus 1/2 minus 6. So that's equal to, minus 6.5, right? And so that's going to be, down here someplace, right? So minus 6.5. And that's going to be a point. And that's where the concavity changes. So it's concave down, there, concave down, and then it changes to concave up, like so. Should that be going? Yeah, it should be going through the origin. I just drew it and I missed the first point that I put down. I'm sorry. Here. Yep. Oh, geez. Oh, goodness. There we go. Inflection point. Label these things. If you label these things, then we have harder time arguing with you. Critical points. All right. If possible, okay, if possible, oh, 7, find the inflection points. We did that. 7, find. Eight, oh God. If possible, find the x-intercepts. What does that mean to find the x-intercepts? Yeah, not where x is 0, or y is 0, right? So that means solve this thing's equal to 0. Now we could do that. Let's not right now. And that would tell you what this point, and this point is. All right? The issue, here's why I don't want to do it. It's because, well, first of all, it just comes down to factoring out the x and solving a quadratic equation. We already did that today. Not the same one, but we did that today, so that's good enough. Second of all, one of the points of curve sketching is solving equations is hard. When we do curve sketching, we want to solve as few equations as possible, and hopefully when we take the derivative, solving that equation is easier than solving the starting one. Does that kind of make sense? That's sort of the point, at least in my mind, that solving equations is hard. 8, find horizontal, find roots. Find roots. 9, find horizontal asymptotes if there are any. There probably aren't. 10, you should determine an interval. That shows relevant, oh God, behavior. So I guess we could, no, let's find the roots and then be done with it. All right. So how do we find the roots here? It's a cubic. I'm going to erase this. And then we will have sketched the heck out of this curve. We want to solve, so find roots. We're going to get 2x cubed minus 3x squared minus 12x equals 0. What's the first step? Factor out that x. If you can't factor out the x, you're in trouble. All right? You might be able to solve that cubic, but you're really in trouble if you can't factor out that x. So factor out the x. So we have x equals 0 is 1 root. We already knew that. It's right there. Right? So now we factor out the x. We got 2x squared minus 3x minus 12 equals 0. Now what do we use? We use the quadratic formula. We could complete the square, yeah. We could. But let's use the quadratic formula. X equals, okay, so something over 2a negative b, 3 plus or minus the square root of 9 minus 4 times 2 times 12 negative 12. 4 times, so minus 4 times 2 times minus 12. X is equal to 3 plus or minus, oh my god, 4 times 2 is 8. Four times 2 is 8, times 12 is negative 96. So 9 minus negative 96 is 105. Plus or minus the square root of 105 all over 4. Oh my god, what is this? Well, the square root of 105 is about 10, right? So 3 plus 10 is 13. 13 divided by 4 is about 3, a little bit bigger than 3. So your other root is around here at 3-ish. 3-ish. And this one over here, square root of 10, 105 is about 10. So it's going to be 3 minus 10, right? That's about 7 divided by 4 is a little bit bigger, a little bit smaller than 2, right? 2-ish. This is like 2-ish here. 2-ish. And so a good interval would be 2 to 4. If we plot this on the interval from negative to, let's make it negative 3. Negative 3 to 4, we would get all the necessary behavior. Does that make sense? Ask a question. If you have any questions at all, just ask. Yeah? Yeah, because this is supposed to be negative b, right? So it's negative negative 3. And here I squared it so the negative went away. He asked me where that negative sign in front of the 3 went. What other questions do you have? Yeah? So I'm sorry, ask one more time. Yes. To find the inflection points, you set f double prime equal to 0. Once you do that, it doesn't mean that it's an inflection point. How do we figure that it was, right? How do we figure out that this was the inflection point? The inflection point is where the sign of the second derivative changes. So, I'll get this, okay? 12x minus 6, it's a line. What's the slope? 12. It's a really slopey line. It's like this, right? Here, this is the oh, it has to cross, oh, stupid Bart. There we go. Now, there we go. So here it is. Here's negative. There's the Y-intercept, negative 6, right? It crosses. This is that x equals 1/2. Now look, to the right of this, it's positive. To the left, it's negative. The second derivative changes sign. If the second derivative looked something like this and just grazed the x-axis, then it might not have changed sign. All right, so how do I imagine? Well, I wish I had the type of question that I'm imagining available. Let me just check and see. Maybe your book has exactly what I want. Yes, it does. So my favorite question is like this. So here's how this could happen. Oh yeah, I'm sorry. How did I get this right here? Oh, I solved for this equal to 0, and I estimated. I don't have a calculator standing. If you guys are taking the test, you could just plug this in your calculator, get a number out, and be like, bam. Instead, I had to do some sort of estimation, and I did a really crummy one. What I said was this is about 10, so I did 3 plus 10 is about 13. 13 divided by 4 is about 3. Every step of that arithmetic was wrong, okay? But it was all close, sort of. Yeah?
On the graph, what's the lowest point on the y-axis?
What's the lowest point on the y-axis? She can't read this right here. Yeah, negative 20.
Where did you get that from?
Where did I get this from? What I did was I plugged in my critical value right here. So I plugged in 2 to here. And I got 2 cubed is 8, times 2 is 16. 2 squared is 4. So 16 minus 12 is 4. I'm kind of going straight across. So I got 4 so far, right? But 4 minus 12 times 2, negative 20. That's how I got it. So if you're lucky enough on a test, we could give you something to sketch that's like this. But the thing is that you guys all have graphing calculators, right? So your strategy as a student, I mean, this is the good one, right? Is you plot it with your calculator, and then you just draw whatever you see, and then you kind of make up some stuff, right? And so then we have to watch your work. So if I was writing the test, which I'm not, but if I was, I would give you one of these, okay? Are you guys ready for this? This isn't that hard. It's actually an easier problem, if you ask me. We're going to do number 22 from the book on page 238. And I'll write that down in just a second. For 22, page 238. All right, here's how it works. They say sketch the function on 0, 4. And here's what they tell you about it. F prime of 1 and F prime of 3. Oh shoot, I'm reading the wrong problem. Okay, let's try again. I'm sorry. F prime of x equals 0 at x equals 1 and 3. F prime of 2 is undefined. F has neither a local maximum nor a local minimum at x equals 1. So no local extrema at x equals 1. And F has an absolute max at x equals 3. Let me just make sure I got all this. I'm going to read it again. So F prime of x equals 0 at x equals 1 and 3. Okay, good. F prime of 2 is undefined. Okay. F has an absolute maximum. No. Oh, I forgot that one. F has an absolute max. Oh, this should be absolute min at x equals 3. Absolute max at x equals 2. Okay, so F prime of x equals 0 at x equals 1 and x equals 3. F prime of 2 is undefined. F has an absolute max at x equals 2. F has no local max nor local min, no local extrema at x equals 1. And F has an absolute minimum at x equals 3. Did I get all those down someplace? We're supposed to sketch F now. Does your calculator help you? Go ahead. Has a min, sorry, has a min at 3 and a max at 2. Mix has, yes, you have to change 2 letters to get from min to max and max to min. Okay, so your calculator doesn't really help you with this sort of problem. You have to understand what it means. But on the other hand, that kind of means that this problem is kind of easier because you don't have to do any calculation. At least I don't think you do. All right, so let's go ahead and try to sketch this. What interval are we on? 0 to 4. So let's draw this correctly, Bart. Y, x, 0, 4. Okay, now let's see, critical points. F prime of x equals 0 at x equals 1 and x equals 3, right? So 1, 2, 3. So here's a critical point, right? F prime of x equals 0 at x equals 1 and x equals 3. Awesome. Those are 2 critical points. Oh, and F prime of 2 is undefined, right? So it's undefined there. We have an absolute max at x equals 2. An absolute max. And we have an absolute min at x equals 3. All right? No local extrema at x equals 1. Right? Okay. So here's what our function has to look like. I'll color it in hot pink. Well, how about I propose something and then we run through and see if I'm right or wrong. Since f prime of x equals 0 at x equals 1, but there's no max or min, do you know what the function has to look like if it's equal to 0 but there's no max or min? Yeah, it has to look like x cubed somehow. It has to look like this. And so we'll go ahead and it looks like that. Maybe even a little flatter. Maybe I should make it even just a little bit. There we go. How's that? Right? See how it flattens out? But it's not a max or min. Now, f prime of 2 is undefined. So how can derivatives be undefined? Yeah, you could have a cusp. And plus, since it's a max, right, that's kind of ideal for a cusp. We don't know anything about the second derivative, so it's going to look something like, boom. Oh. And since this is an absolute min, this thing had better cross, right? Be like here. above the min at the end point. And this thing had better cross right here, also at the end point. What do you guys think? Does this fit the bill? We can go back. Yeah, please. The max has a sharp corner. And you know what you could do? You could label. You could be like sharp. We call that a kink. What do we call that? Pointy. Pointy. Okay, so we're on the interval 0 to 4, check. F prime of x equals 0 at 1, check. F prime of x equals 0 at 3, check. F prime of 2 is undefined, check. No local extrema x equals 1, that's correct. Absolute min at x equals 3, check. Got to make sure this one's lower than over here. Absolute max at x equals 2, done. All right, so how could we make this problem even more? What could we do to make this problem even more challenging? Any ideas? Give you more information. What other information could we give you? Yeah, we could put in more extremas, or we could put in more. We could give you more. We could give you more. Here we go. Designer functions. Okay, so let's do this one. This is the one that this one's going to be great. Okay, so what questions do you guys have about this one? Good. Here we go. Here we're going to do number 90 on page 253. Number 90 on page 253. It looks great. My favorite. 90, page 253. All right, here we go. F double prime of x is equal to 0 from negative infinity to negative 2. F double prime of negative 2 is equal to 0. F double prime of x is greater than 0 from 4 to infinity. All right. That should be easy, right? All they gave us was this information about the second derivative. I meant greater than, I meant less than 0. Whoa, wait. It's greater than 0 on this. Oh, geez, there's more writing on the page. Okay, let me try this one more time. So f double prime of x is greater than 0 on infinity, negative infinity to negative 2. That's right. F double prime of negative 2 equals 0. Check. F prime of negative 1 equals f prime of 1 equals 0. My God, Bart can't read. F double prime of 2 equals 0. My God, there's so much more there. It's written small, guys. F prime of 3 equals 0. And then f double prime of x is greater than 0 on 4 to infinity. Okay, I'm going to read it one more time. Let's make sure I have everything, and then we'll be all set. Here we go. I'm sorry, this is so boring. Here we go. F double prime of x is greater than 0 on negative infinity to negative 2. Check. F double prime of negative 2 equals 0. Check. F prime of negative 1 equals f of negative 1. Sorry, f of 1 equals 0. Check. F double prime of 2 is equal to 0. Yes. F prime of 3 is equal to 0. Yes. F double prime of x is greater than 0 on 4 to infinity. Yep. Looks good. We happy? All right, let's sketch it. Oh, we're supposed to sketch this on the interval negative infinity to infinity. Okay, great. What should we mark off first? We have all this information. What would you guys mark off first? Critical points. I like marking off critical points first. Critical points would be great. So I have critical points at -1 and 1, right? And someplace else? Oh my God, yeah, 3. Okay, so -1, 1, and 3. So here's 1, here's 3, there's -1. Okay, so there are my critical points. Now, I want to know if these are maxes or mins, right? And so, do I know anything about the second derivative at -1? Okay, what's the second derivative at -1? Where does it say that? We don't know anything about -1 here. All we know is that the derivative is 0, but we don't know anything about the second derivative. Did they not tell us that? Second derivative 0 to 2, -2, f double prime of 2 is equal to 0. Yeah. Yeah, they don't tell us anything about the second. That's fine. Okay. What's the other? Oh, f prime of 3. Oh, you bastard. Okay, that's fine. What do we know about the concavity about here? So at f double prime of 2, let's put the possible, let's look at the concavity at 2. So here's 2. So what do we know about the concavity at 2? Yes, please.
For -1, would it be a minimum point on the fact that f double prime of x is less than 0 before that? Would it be a minimum? Because it concave down?
She's saying f double prime of here?
Yeah.
She says, hey, it's concave down. It's concave down here, right? So, well, let's draw it. That's kind of what I want to do, right? Yeah. Let's see if we can conclude, right? So it's concave down to -2, right? So to -2, your function's concave down, right? There's a concave down, and then what do we know? We know it's concave. We know the concavity could be changing. Could be at -2, but all we know is that it's 0. And then, let's see, f double prime of x is greater than 0, so that's concave up from 4 to infinity. Concave up looks like this. Looks like, draw it better, Bart. There, it looks like that. What other places do we know the concavity at? F double prime of 2 is 0, so the concavity is changing here. So it could be going like this, or like this. And then, what's happening with the concavity at -2? It's also changing. I think I know why this exercise is called designer functions. Yeah, go ahead.
Why is the concavity as the del prime of x is greater than 0? Greater than 0, yeah. Oh.
Thank you. He says, hey, your graph's not right. What's greater than 0 mean? It means it's concave up. There we go. Right? So it looks like this. And then the concavity changes at -2, right? Well, it could change. It's 0. So what type of, and then we know that these are critical points here. So this is supposed to be, so we're just supposed to draw a function that satisfies this. We're going to have some choices at this point. So if this is a critical point, there could be a local, there could be, all we know is the slope is 0 here. The slope is 0 here. And let's go ahead and make the slope 0 here. And so see if you agree with me. I'm going to finish off a function. And tell me if you agree that this would satisfy the conditions listed here. The concavity changes. So if it's concave up here. Well, I want to do this. Oh, yeah, I can do that. So put this down here. And then we're going to have the concavity change again. And go like this. Concavity change right there. And we could have the concavity not change right here. This would be a function that satisfies what's going on here. What do you guys think? Yes, ask.
How did you know the slope is 0?
Okay, I knew the slope was 0 because I have the critical points right here. F prime of -1 equals 0. F of 1 equals 0. But what I don't know, what I drew in pink there, I actually don't know exactly what the curve looks like. The exercise is giving me choice. Okay? Go. It just has to touch anywhere on that line. It has to change concavity. Doesn't have to go through that point. All right, we're done for today. If you have a question, come ask me.